Okay. First, let me.
So what happened with your cruise?
The cruise got canceled, but I got a 225% credit for a future cruise. So I got 2.25 cruises for the price of one.
What do they kick you off the? What if they kick you off the boat if you like for the 2.25? Do they like just take you to like one?
Well, no, I mean they told us like 2 days beforehand, so we hadn't even flown down. We were pretty much assuming they were going to cancel it, so we hadn't packed or anything.
Yeah.
All right, let's see. So grades on the exam. Looks like the class average was right around a 70. High grade was a 100. Low grade was a 30. So kind of the usual, all over the place. If you, performed way under where you think you should have been, remember you have the final exam to repair that. Otherwise, if you just think the stuff is, I wouldn't recommend anybody, well, except maybe the 30 to consider dropping the class, but outside of that, I think everybody is in reasonable shape. So let's go over the exam. Oh, I have to do it this way. Pretend like I'm editing the test. There we go. All right, let me share my screen. Let me move all of you back up to the top. Yeah, so when you see me look up, it's because I have you on my top screen. And I'll get, so as usual, just blurt something out if you have a question. I technically can still see chat now because I can move it up to the top screen. So I'll try to keep an eye on that, but for a small enough group, just blurt it out. All right. So everybody can see my screen? All right, so let's start going over the exam. All right, so first one should have been a softball. Why are arrays considered to be fast and memory inefficient, while linked lists are considered to be slow and memory efficient? So arrays are stored in contiguous memory so that elements of the array can be directly accessed by calculating the exact location in memory by using the base address and an offset from that base address. All right, so this makes them fast. Because they require contiguous memory, we have to ask for all the memory up front and right next to each other. Means we have to have enough contiguous memory to hold our data, not just enough total available memory. Makes them memory inefficient. All right, that part makes sense for the array side of it. So something along those lines. So linked lists are stored with a pointer to the very first node in the list, with each node knowing where the next node is in memory. So only the amount of memory that is currently needed to hold the data needs to be allocated, and it does not have to be contiguous. This makes them memory efficient. I know I'm doing the memory and the speed thing backwards on the linked list, but whatever, all the data is there. Because they are not stored contiguously, we cannot calculate the exact memory location of a node. Therefore, we have to traverse the list until we get to the node we want. So from beginning until we get to the node we want. This makes them slow. So something that captures the essence of, did everybody notice how I just like paused there for a second? It's because I glanced up and saw Clancy's picture. How old are you in that picture, Clancy?
It's my senior picture, so that would have been 2 years ago. It's like the only like nice photo I could find of myself on my computer. So
I just thought that was pretty funny that I looked up. That actually was the distraction. It didn't look bad, but I mean, it didn't look good.
Oh, thanks. Appreciate that.
All right, so any questions on this one? This was actually missed more often than it should have been. This should have been pretty obvious. You had to say the word contiguous somewhere in there. I mean, you didn't have to spell it out in this level of detail, as long as you generally convinced me that you understood the difference and you kind of said the right bullet points. That was fine, but
What bullet points specifically were you looking for? Because I got like an 8 out of 10 on it. So, were you like this? What points do you specifically want us to highlight?
well, if I'm going through this, I mean, definitely that arrays are fast because of contiguous memory. And arrays are memory inefficient because of the same reason, the contiguous memory. They have to be allocated all at once. Linked lists are slow because they are not necessarily stored next to each other. So the only way to get from one node to another is by asking a node who his next node is. And really the reason that they are memory efficient is that they're not stored in contiguous memory, and we only need to use the amount of memory that's exactly the size of the linked list currently to hold its data. So I guess, I mean, I'm not necessarily looking for exact words, although contiguous would have been a word that needed to be there. So I'd have to look at what you have. If
It's just from my response. It's just from my response. There was no feedback given, so I was confused.
if I took points off, there should be feedback.
It's just, yeah, nothing. I'll look again, but
Okay.
pretty sure there isn't.
Just to make sure I have feedback turned on. Other people saw responses to like why I took points off? Okay, yeah, because I think pretty much every
Yeah.
time I took points off, I gave feedback.
It was weird for mine because that was the only question where you didn't give feedback.
Okay, well, I can look at it. It's possible that it was just mostly right, but not quite all right.
Yeah.
But I'll take a look at it. I can give you some explanation. All right, so next one. And again, we kind of have to write this abstractly because we don't have the actual thing sitting in. I said make the assumption that we have a stack class and things like that. I guess with this one we can write it for real, but so create a class representing student objects. A student has a name, email, and GPA. Make sure to include all the necessary constructors and getters, setters. So if I just jump over here, oh, that looks beautiful. What is that? Just do that. Let me open the folder for us. All right, I'll just create a quick folder called midterm. All right, we'll create a new file in here. And who are we writing? We're writing student objects. So we'll call this guy student HPP. All right, so inside this guy, we're going to create our header file, which should give us kind of our high level version of this. So we're going to have our class student. And inside of this, we're going to have a public section. Well, we'll have a private section and a public section. All right, and we're supposed to, a student has a name, an email address, and a GPA. So we might say name and email are strings. We could say GPA is a float if we wanted to, or a double. If you wanted to store them all as strings, you could do that. That's more of a dealer's choice type thing. It ultimately comes down to how do you work, what are you going to do with the GPAs? But let's just say we're going to store them all as strings. So up top, I didn't take off for this, but you want to include the right stuff for doing your strings. But I didn't look at that, just as long as you gave me something to look roughly, what it was supposed to be. So we're going to have a string. What was it? Name. A string email. Actually, what's this guy in? And then we have a, here I'm going to do it as a double GPA. All right, so those are going to be the fields that we're going to keep track of. And then for public, we need our constructor. So we're going to have a constructor for student. And this guy's going to take in a string name, a string email, and a double GPA. And then we need getters and setters. So we want to have a string get name, a string get email, and a double get GPA. And then also setters, although if you didn't give me setters, that was fine. So if you just ended up at this, I would say that's okay. but we'll go ahead and create the setters just to be complete here. So we'll say void set name is going to take in a string name. Void set email will take in a string email. Void set GPA will take in a double GPA. All right. So that's the header file for this guy. Now, many of you stopped right there. There's no implementation yet. we haven't written any code. So this is kind of reorganizing the question into a code structure, but we haven't actually implemented any of the pieces yet. All right. So from this, we actually have to go and write our stuff. So I'll create another, where's my midterm? There we go. So we'll create a new file, student.cpp. Inside of here, oh, I didn't need the private section. I'm going to include student HPP. Go ahead and give me my skeleton thing here. Whoops. Okay, so constructor, go ahead and set this name equal to name, this email equal to email, this GPA equal to GPA. So that's it for the constructor. Get name is going to return this name. That's it for that. Get email is going to return this email. That's it for that. Get GPA is going to return this GPA. That's it for that. Set name will set this name equal to name. Set email will set this email equal to email. And set GPA will set this GPA equal to GPA. All right, so that's the actual implementation that I'm looking for. Again, if you didn't put the setters in there, that's fine. So if this is what you had, you showed me that you understood how constructors work and what their job is, and then roughly the idea of, hey, I need to access these private members, these private fields of my class. All right, so people who missed points on this one gave me this. A couple people gave me even less than this, but most people at least gave me this. The header file isn't the implementation. So you needed this part to actually show me what they do. Questions on that? Oh, Ninja. Okay, so let's keep trucking. And I can post that up to I'll post it at the end. I'll create a GitHub for it at the end. So I'll just create some different files in here, if that's cool with you. There, we'll say C GitHub code. All right, next. Oh, convert a thingy. Oh yeah, some of you forgot the trick. It must have kind of sucked. All right, so it's a Brockers smirking. All right, so I specifically picked binary to hexadecimal because you can work with groupings here. So we have 1101, 1100. Nope, apparently I don't like zeros today. And these are groupings of 4 because hexadecimal operates in, you can represent the entire hexadecimal vocabulary, all the hextets, using 4 bits. So this first guy, this is 8 plus 4 is 12 plus 1 is 13. So that's a 13. And this is a 12. So this is a D. This is a C. So your answer is DC. That makes sense? I would say for the most part, people got this one right. But I would say too many of you had substantial work that you were showing for this one, where you were converting from binary into decimal and then decimal into hex, and you ended up with the same answer. But by this point, you should understand that octal and hex, the reason those are popular computer bases is because they're powers of 2, and they allow you to have this convenient conversion between binary, which is our machine language, and those specific bases. Octal can be in 3 bits, because you can, the entire octet vocabulary can be represented in 3 bits, 0 to 7. The entire hextet vocabulary can be represented in 4 bits, which is 0 to 15. And actually, the next one would be a 32, which would be base 32, which does have a name, but I don't remember what the name is. So you can represent the entire vocabulary of that one in 5 bits, 0 to 31. All right. So once our computer memory and stuff gets even larger, we'll eventually bump up to, and it's possible we'll never hit this because we'll end up being in quantum computing or something before that. But our next available slot for easy conversion between binary and a base would be base 32. So it's going to be a power of 2 base. This would also work for base 4. So we can represent base 4 in 2 bits. All right. Questions about that one? I'm assuming probably not. All right. Error-free Hello World program. Again, I didn't care about whether you included the right stuff, but so you would have included IO stream.h. You can say using namespace std. And then you would say something like int main cout hello world. You could put a carriage returned in there if you wanted. So something along those lines. Several people also put in, you know, like a return 0 there, which is technically correct because we have advertised that the function will return a int, but it would still run without you returning something. So something along these lines, but I think in general, most people got this one right. So that was good. That's making that jump from Java mentality to C++, not really having to rememorize this, but to remember that you know, all programs begin and end with main, and you remembered the structure of main. So I think that one went fine. Questions about that one? All right. All right, so this one was missed too often. We talked about it several different times. So what is the this keyword and why do we need it? So we'll start off with the obvious thing of this. So this is how an object refers to itself from within itself. We need it because within an object, we do not have access to the variables external which reference this object. So we need this special variable to talk about ourselves. So that's the what is it and why do we need it. Then the arrow syntax. So for instance, if we say like this dot this arrow numerator, this guy is shorthand for star this dot numerator. So the arrow resolves a pointer to its value and then calls a member, simplifying dot notation. All right, so when we want to, so we can't say this dot numerator because this is a memory address. Star this is the value that lives at that memory address. And we can use the value that lives at that memory address to access one of his members. What the arrow gives us is a convenience so that we don't have to constantly be writing this parentheses star something. Instead, we could just say, I'm going to use an arrow here, so I'm implying that I want you to resolve this pointer to its value and then call its member. That's what the arrow implies. All right, questions on that one? All right. Let's see. Write a method. It takes an array of ints as a parameter, reverses that array in place. That is to say that your method does not return a value, but rather updates the existing array to be the reverse of itself. Okay. I'll go ahead and write it over in over here. Let me just call this. Well, you know what? I'm going to write it just inside of student CPP, and then I'll just copy it over. Okay, so this guy is going to return nothing. And it's going to return nothing because we are updating that array in place. We're asked to take an array of integers as an input and reverse that array in place. So we're not returning a new array. We are updating the array that was passed to us by address, right? Arrays are passed by address to be at the reverse of itself. All right, so it's going to be void. We'll call this reverse array. It's going to take a int pointer AR as a parameter. And then you probably also wanted to take in an int array size, something like that. Some of you did like the, the math thing, the size of thing, and that's fine. I gave you credit for that, even though we saw that that could have a little bit of an unpredictable result depending on how you're working with it, but it was fine. I mean, so as long as you didn't like pretend like AR had a length function or something like that, that was okay. So what I'm going to do here is I'm going to create a int temp of array size. So I'll just create a temporary array of the same size as the original one, and I'm going to go through my original array. So for int I is equal to array size -1, I is greater than or equal to 0, I minus minus, and I'll say temp at bucket. You could do this actually with a single for loop, but I'll actually just write it with an external one. So pause, I'll start off at 0. Temp at bucket pause is equal to AR at bucket I. And then I'll say pause plus plus. All right, so when that for loop is done, temp is filled up with AR in reverse. Then I'll just write another for loop real quick for int I is equal to 0. I is less than array size. I plus plus. AR at bucket I is equal to temp at bucket I. All right, so that will reverse the array. Several of you did, a fancy thing where you tried to go up just to the halfway point and kind of flip-flop stuff. That's all fine and dandy. No, nothing wrong with that. But you're in a test situation. You also want to get a correct answer first, not really worrying about optimizing it. Arrays are already fast, so this is probably not something that we're necessarily worrying about. So I just created a temporary one, filled it up with the original one in reverse, then went back through and copied those values back over the original. You got a reversed array. So using this as a good example, I'd encourage you to approach problems like this. When I look at the exam and also some of the conversations I've had with some of you outside of class, your mind is immediately trying to come up with this like weird, complex solution to things. You immediately think, oh, well, do I need to use a linked list that, a doubling linked list that does this, that, and the next thing? Think about what is the simplest solution that will give you a correct answer, regardless of how boring it seems, regardless of how repetitive it seems. Get a correct solution first. Then you can look at it and say, is this embarrassing? And update it if necessary. Okay? So this is a very straightforward way of answering this question without doing all the fancy, counting stuff like I minus J, or only going up to the halfway point where you're sitting there drawing pictures and deciding whether or not did I miss a bucket somewhere in there. You're not going to miss any buckets this way. You just do them all and then you do them all again. All right, questions about that one? So let's see how this ends up copying across. Yeah, not so hot. Well, actually, I bet you maybe would have been okay if I do that. And then I left justify. Yeah, that looks okay. All right, so there's that guy. Next. All right, so this is where we're going to have to make some assumptions because, I said you assume you have some things. And as long as you made reasonable assumptions and, you didn't assume that there was a method that literally solve the problem. Just like do question 8.
Sounds reasonable to me, though.
All right, so assuming you have access to a linked list of events, similar to what we wrote in class, write a method that takes a linked list as a parameter and removes all of the odd numbers from that list. You may assume that you have access to the following methods: add front, add end, added index, remove front, remove end, remove all, remove an index, get count, get an index. All right, so here, I'll write it over here and then copy it over. Hopefully this guy, it's good. Keep in mind, we're going to have some squigglies because we don't have our link list in here. So we're going to have let me just make sure I'm saying this is a parameter and removes. Okay, so we're not returning anything. We're removing the thing in place. So we're going to call this guy remove odds. He's going to take a linked list LL as a parameter, probably a linked list pointer. All right, and keep in mind, we're going to have some squigglies in here because we don't have a linked list that we've written for this, so just deal with it. All right, so what we want to do is we want to go through every element of this linked list. So we'll say for int I is equal to 0, I is less than, what I say, get count, LL get count, I plus plus. Then we want to ask a question. If, and we have a get at index function. Now you can make the assumption that get at index gives you the int value that's in there instead of the node. That's fine. That's what I'm going to do here. So we're going to say if LL get at index I when modded by 2 is equal to 1. If it's an odd number, what do I want to do? I want to say LL, what do they call it? Remove an index? Remove an index. LL remove at index I. So if it's odd, I want to remove it. All right. But if I remove something, my count, my list now has 1 fewer things in it. So since I just removed it, my indexes just shifted. So I need to artificially shift my count. So the next time through, I'm going to actually check the same bucket I again, which is actually now a new value, because I just removed the old thing that was at bucket I. So now the guy who came after him is the new thing at that same bucket I. So since I removed something, I need to artificially change my count because it's about to increment again afterwards. All right, so go through every element of my list. Ask if the current element is an odd number. If it is, remove it and decrement my count so I check the right bucket the next time around. When this thing is done, LL should now have all the odds removed from it. Question about that one?
So whenever you say that you can use a method, like you can use a selection of methods as long as you follow the parameters of that method that you have listed, it's good. You don't have to actually write out the method.
Correct. Yeah, I said you assume you have these.
Okay.
You have access.
Basically like tools.
Yeah.
Like tools of
you already have.
Okay.
And as long as you make a reasonable assumption. So some of you might have said LL get an index, and then maybe you wrote something like get payload if you wanted to get the value from that. That's okay as well if you assume that get index gave you a node instead of the actual value. But if you just wanted to assume it gave you the value, that's a reasonable enough assumption. So I wasn't nitpicking on these things. You know, but I would say LL remove odds would not fly.
Wouldn't remove at index have a count decrementer in it?
Exactly. So remove an index would decrement count. So this guy would now return a different value. So I need to change my value of I so that I don't skip a dude.
Okay. Okay. That makes sense.
Yeah, you're absolutely right. That's why we had to do this.
Okay. That makes sense.
Okay.
Yeah, and I didn't take off much for that. So there was plenty of people who got this pretty much correct like this, but forgot this one part. And I knocked you a couple of points or something, because I mean, that's an integral part, because the piece there is understanding that dynamic data structures like linked lists, when you change them, their structure is now changed. And if you're relying on some hard-coded value like get count, you'll have a problem. And actually, if you're using like a for each loop, in like Java, if you have a linked lists are something called iterables. It follows the interface of something that's iterable. So you can actually say for, something like for node n in LL, something like that. So in Java, you can do that. So each time through, n will be the next value inside of LL. But if you try to inside here, say remove at index 2, this is going to give you an error. It's going to give you an error. Basically, it's going to say you're in the middle of iterating through this linked list, and removing something will break that iterator. Because now you have a different number of elements in the list than you had before. So languages like Java guard against this if you're doing a for each loop through every element in there. We're seeing the situation for us where we're having to say we have to self-police. Since we're going through every element based on a count, or if we were going through it by looking at next nodes, we would still have to say, oh, if I remove something, my number of elements is now less. I can either say it's illegal to check again and just break out of here and keep going through it over and over and over again until you finally run out of odds. Or I can say I'm going to play a math trick and just make sure I check the same index again the next time through, because my new index is the next guy. All right. Number 8. Oh, yeah. Seems like you guys have mentally blocked out the recursive nature of merge sort. It's a dramatic experience. Remind me, what does it mean for a function to be recursive? What does recursion mean?
A function to call itself within itself.
Yeah, it's a function that calls itself from within itself. So recursion is when a function calls itself from within itself. So like merge sort was one of those guys. He actually called himself twice from within himself. All right, so assuming there exists a linked list object that's capable of holding ints, you can make reasonable assumptions regarding the methods that each of these data structures already have. So we're writing a recursive structure that takes a stack, which is a specialized version of our linked list, right? Stacks have what functions? Push, pop, peek. All right, and it prints to the screen the contents of the stack. But we're writing a recursive function. Okay, prints to the screen the contents of the stack. You do not have to preserve the contents of the stack, so we don't have to worry about the stack staying in any sort of good shape. All right. So we're going to say void print stack. This guy will take a stack pointer s as a parameter. And we'll say if, you can decide how you want to get a count, but maybe we say s get count, greater than 0. Similarly, you could say if S peak is a thing, either one of those will work. So if S peak is a thing, then we can say, we can pop it. So we'll go ahead and say C out S pop. And if we wanted to kick it down a line, you know, we can put in a \n. Did I say print it 1 per line? Screen the contents of the stack. Yeah, I didn't say how to print it, just print the contents of the stack. So I'll pop the top of the stack off, which does remove it. Do a carriage return. I'll print that out, and then I'll call print stack again, passing it S. So print stack takes a stack as a parameter. As long as there's something on the top of the stack, pop it and print it, and then call print stack again, passing it the same stack that now has 1 fewer things in it. We ask the question, does it have something at the top? If it does, pop it and print it. Print stack again. As soon as we come in here and the stack is empty, the function ends. So there is a recursive version of printing a stack, paying no attention to keeping the stack in shape. Questions about that one? Several of you wrote iterative versions of this, you know, like while stack has more, while S peak, you know, you would print it out, and then, so you wrote it like this. While S peak, C out, S pop. You wrote something like that.
I have a question.
Yep.
Did we already have recursivity like on a slide? Because I could not.
Did we have recursiveness on a slide?
Yeah.
Not this semester, but I mean, recursion, something we've done for a year.
Okay.
Yeah. Yeah, so at this point, the idea of recursion should be something you should just know.
Okay.
It's not part of 300 specifically. It's just part of programming, like a for loop is, or something like that. All right, so some of you wrote something like this, which is fine. That's not incorrect logic, right? You know, that will print out that stack, not preserving it. You know, so that was fine. That's worth points, but you missed the recursive part of the question. All right. Okay, so next. Assume there exists a linked list objects that are capable of holding ints, that is capable of holding ints. You can make reasonable assumptions regarding the methods that each of these data structures already have. Write a method named reverse list that takes a linked list as a parameter and returns a new linked list, so a brand new one that is the original one in reverse. Okay, so takes a linked list, returns a new linked list that is in reverse. So we'll call this guy get reverse of list. This guy will take in a linked list pointer, LL as a parameter. All right, and what we want to do is we want to walk through this entire list. Now one thing, so I'll just point something out that when we write objects and we give ourselves these nice functions like, you know, add end, get front, get at index, all these things, these are conveniences, right? That means that we no longer have to go through like cur node and go to cur node's next node and things like that. That was already implemented. We wrote those things behind the scenes. That's the purpose of object-oriented programming. That goes back to that idea of a telephone. If you're using a telephone today, you pick up your smartphone and you just start pushing buttons, as opposed to the procedural version of a telephone. You have a big pile of wires you're fishing through and you're working with all those details. Okay, so too often on the exam, I had all sorts of, you know, syntax dealing with nodes and next pointers and things like that, when we already have these nice functions that do all that work for us. We don't have to worry about that. All right, so I'm going to create a linked list pointer. We'll call this guy answer, and he's going to be a new linked list. And then we're going to go ahead and go through every element of our current list. So we'll say for int I is equal to 0, I is less than LL get count. That's a reasonable function, I plus plus. All right, so we'll go through every element of our first linked list, and we're building our next linked list in reverse. So we'll say answer add front of LL get at index Now, this assumes that get at index gives us the number, not the node. All right, so we're going to add to the front the number that is returned by get at index I. If you assumed it gave you a node, you would have had to do something like get payload here. All right, so we'll say answer add front to LL get at index. That will end up having us build answer as the reverse of LL. Then we'll return answer. We'll go through every element of LL, take each of those elements and add it to the front of answer, which will build answer up in reverse, and then return the new linked list. So this guy's not void, he's a linked list pointer. So we'll return answer. Make sense? All right, so for several of you, this was way more complicated than it needed to be, with all sorts of node, pointer, cur nodes, and spinning up to certain things. Those are all, that's all good syntax that we've already written inside those functions. We already put in our reps, we put in our effort to write those. Now we can just use these nice functions like get count, or get at index, or add front. These are all nice, convenient things that allow us to now use that tool that we've built. All right, questions on that one? All right. Last but not least, assume there exists a linked list objects that are it's just bad English. Where were you on that one, Clancy?
Hey man, I'm a computer science major, not an English major. That's all I gotta say.
Same here. So capable of holding integers. You can make reasonable assumptions regarding the methods that each of these data structures hold, blah, blah, blah. Write a method named remove at index that takes a stack and a zero-based index as a parameter. And it should remove the element at that index in the stack, leaving the rest of the stack intact. So for this problem, we're assuming position 0 is the top of the stack. So just like an array. All right, so it's remove at index that takes a stack. So this guy is going to be void remove at index. It's going to take a stack pointer s as a parameter, as well as a int index to remove. All right, so what I'm going to do is I'm going to create a temporary stack to hold all the values except for that index. So I'll say stack pointer temp is equal to new stack. So I'll create myself a nice stack. Then I'll say for int I is equal to 0. I is less than index. Index to remove I plus plus. We'll say temp dot push, or temp push s pop. All right, so we'll push pop down to, but not including the index we're going to remove. Then we'll say s pop. So that'll remove that guy we want to get rid of. So I have everything before him stored in this temp stack. Then I've gotten rid of the guy we want to remove. And now I'll go back through and say, while temp peak, while that guy is a thing, what am I going to do? I'm going to say s push temp pop. So temporarily store everything before the index I want to remove the index, then pop everything off of temp, pushing it back onto the original stack, giving us s put back together with that one element removed from it. So we're using the tools that are stacks to do push, pop, and peek to make this work. And this was probably the biggest culprit of people trying to wire together the whole next node and things like that, going through and saying, okay, I'm going to go up to this one point here, and then I'm going to do the surgery by taking the guy before him and the guy after him. I'm going to sew them back together, getting this guy disconnected from it. That's all fine and dandy. That's how like remove an index would work in a linked list, but we've already written those things. We were already given those reasonable methods that we've written. So now we can just use them and have a nice, powerful tool. So hopefully most of you see that this is significantly more concise and easy to follow than what some of you wrote, right? So if there's one lesson to kind of get from this, it's this idea that, you know, whenever you're solving a problem using a tool, the only reason we write stacks or linked lists or queues or any of these things, the reason we write them is so that we have this nice tool that we can now reuse. If you go to Home Depot and you buy a table saw and you're using it to cut some boards, every single time you go to cut boards, you don't dismantle the table saw and start dealing with the things on the inside of it, right? You turn it on and start sawing and hope you don't lose a finger. So, you know, that's the purpose of these tools. We have them, they do a job for us, now we use them because we like these power tools. All right, questions on that one?
Yeah. So basically, what you're saying is that that like things like push, the push, and then the index function were things that we could, in theory, use on maybe the final exam.
if it's relevant to the.
Yeah, you can make any assumption regarding, I put it on every single question.
Okay.
Yeah, so make reasonable assumptions.
Look at the time, where I was going too far by using some of them. So it's good to know in more explicit terms.
Yeah, and earlier in the exam, I put one that I gave you like an example of the function, the things you have access to.
Oh, okay.
What was that one? Yeah, here, like, you may assume that you have access to the following methods: add front, add end, add an index, remove front, remove end, blah, blah, blah. And then from that point forward, I said you can make any assumptions regarding the methods that each of these data structures already have. So a stack, push, pop, peek, completely reasonable. Get count, I think, is reasonable as well, but you can get by without get count as well. But if you use get count, that's fine. And I was super flexible as to what I allowed you to use, as long as you didn't use, you know, like S dot answer number 10 as the function. I just assumed somebody else wrote this and it's already correct. And here you go.
So in this question, you specified like that this had to leave the rest of the stack intact. And I didn't make a temporary stack as part of this problem, so I guess I'm not visualizing in my head exactly what temp is looking like and what S is looking like, but I'm kind of confused in the for loop that you're popping and pushing to temp and then you're popping again after the for loop. Like how is that working?
I'll walk through here. Let me actually put it over here. All right, so this is a little temporary stack that I'm going to use just for the moment. And then what this loop does right here is it removes stuff off of S, the stack that you mentioned that I said you have to keep intact, right? So I'm taking stuff off of S, but the things that I'm taking off of S, I am pushing onto temp, so I have access to it. And we can actually go through an example of this. Then I'm burning one more element off of S. This is the guy I'm removing. I'm getting rid of him. So I'm popping him off of S and not putting him anywhere. So he's gone. And then to preserve S, I'm putting back onto S all of the stuff I had in temp. So I just temporarily stored it in temp to get down to the point where I could pop the guy I'm removing off. Then I'm going to pop everything off of temp, putting it back onto S, leaving S in its original form with index to remove gone. So if we look at that as an example here, I have to wait for that to go away so I can. So let's say I have 1, 2, 3, 4, 5. And that's S.
Okay, that makes sense. I totally missed like the while loop that pushed everything back on, so I get it now.
Yeah, well, let me go through this anyways. These are good questions. So this is temp. So temp is initially empty, and let's say that I'm removing index 2. So I'm going to go and I'm going to start filling up temp with so this is going to pop, this is going to pop, but those are pushed onto temp. Then S looks like this. I'm removing index 2. So then I'm going to pop off of S, but not put it anywhere. That gets me that. Then I go through and I pop off of temp. Oh, actually, I put these on backwards because it's a push. We always add to the top. So I push the 1 on, then I push the 2 on top of the 1. All right, so now I'm going to pop off of temp and push onto S. Then I'll pop off of temp and push onto S. So there's my final version of S with everything that used to be there with index 2 removed. And really, I guess a conscientious programmer would say delete temp down here at the bottom. But I didn't take off points or anything for that kind of stuff. All right, that makes some sense. All right, so questions about the exam as a whole.
I wanted to ask about this question again. So that function at the when you do the first for loop, you're basically putting it in like a temporary little thing to sort of like you're pushing it. Like you're pushing it onto, or yeah.
Just show this example over here. If
Yeah.
S originally looked like this, and I wanted to get rid of bucket 2, I'm going to remove the top 2 elements, bucket 0, bucket 1, from S. And
That's what push.
Push them onto temp.
Temp.
To preserve them. That's what that first loop does.
Right.
That first loop will result in something that looks like this.
And then when it goes to pop, then it pops off 2 or 3.
It's rid of that 3 completely. I don't put it anywhere. I just say pop it.
Yeah.
You're gone. I'm not going to use it. I'm not going to store it. I'm not doing anything with it. It's gone.
Right.
After that pop, my stacks look like this.
Right.
And then this last one clears out temp until, so as long as temp has something, it pushes that something back onto S. So I push.
Yeah.
It has a something, so I push it. It has a something, so I push it.
Right. And that would eliminate those things.
Now it doesn't have a something, so this while loop ends.
Okay, that makes more sense.
Okay. Any other questions about the exam? So I would say the exam was probably on the hard side. It probably made you
Want to cry?
maybe, well, no, not cry, but hopefully when you go and see the answers now, you realize it actually wasn't that hard. But as you were going through the exam, and this is, this has been the lesson for the last year and a half, right? That when you're first learning to do this stuff, I mean, think about how impossible these questions would have been for you to solve when you were a 200 student. You would have just looked at it and just thrown up on the page. Pretty similar to what Brocker gave me on his exam anyways. I assume you were drinking the Purell? Is that, but now and if you remember back in 200, I made the statement that, as you go through the classes, I become, in 200, I pretty much let anything go because you're still, you're just getting started, you're supposed to suck, things come really difficult for you. In 250, you get a little bit less leniency because you're still supposed to struggle, but not maybe suck. Well, now as orange belts, we're not supposed to be amazing yet, but we should be able to kind of start these problems and critically think through them and stuff like that. So when you run into, so really this exam is hopefully going to be a pretty good learning experience for most of you. And I fully expect people who did poorly on this exam to do significantly better on the final, because what you learned in going through this exam is you learned that you were doing too much. You were trying to do way too much work to solve these problems instead of just using the tools that were in front of you, right? Part of that is probably going to be your own confidence in your coding. Some of it might be that when you're working in study groups, you're maybe getting a little bit too much help from other people. Some of it might be it just hasn't clicked yet. So the hope is going through this and you see these answers, you kind of had maybe at least a mini aha moment, like, oh, I could have just done that. For like several of these questions where you look at it and you say, I didn't even think it could be that easy. Why wasn't I using the tools that were in front of me? It's because You've spent all semester writing, you spent all semester building a house, right? Working your butt off building these structures. And then when you got to the exam, you chose not to use them. You got to the exam and decided, I'll just build it again. I'll start from scratch. Even though I kept telling you, use things that are built in, use things that are built in. So you just spent a summer building a house and you decided to sleep in a tent next door. But that's good because you'll learn something from that whole process. So, as I was going through here, I kept glancing up and I'm seeing like little eyes, saying, oh, are you serious? So I think that there'll be, this was hopefully what an exam should be, and not a punishment thing, but a learning experience. So you get to see where your shortcomings were. And I think several of you, if you could take this exam again right now, would probably perform substantially better on the exam with this in hindsight. That's why hindsight's 2020, right? But the good news is in my classes, if you got a crap grade on this exam, you can fix it with the final and no harm, no foul. Everything's good. So that's kind of the punchline. All right, any other questions about the exam? Good to go. Okay, so why don't we do this? Go back, and I think our most recent assignment was, what was our most recent assignment? It's been so long. Oh, it was right to have we actually finished the Towers of Hanoi, I think. So we started looking at the shunting yard algorithm, right? And we were writing a stack. So what I'll have you do, just so we can mentally get back into the, so shunting yard is what we're going to be implementing. So for Thursday, look at shunting yard on Wikipedia. Am I spelling it right? Wikipedia, whatever. And gain an understanding of how it works. And actually, I could put up a link to this guy. And this won't be graded, but what we'll do is we'll jump in on Thursday and start writing this guy, and then you'll have a homework over the weekend to kind of finish the gaps. But so study the exam, make sure you understand what went down, and then gain an understanding of how shunting yard works, what kind of problem it solves for Thursday, and then we'll start writing some code on Thursday for it. Sound good?
Yeah, so no official homework for
Nothing that you're going to submit. I'm just going to expect that you're going to come to class with at least a cursory understanding of shunting yard. So if I ask questions about it, I'm not getting a bunch of blank stares. That way we'll dive back into coding, because I assume most of us are kind of disoriented this week with the with everything starting up. All right, but study the exam for things you missed, and if you do have any questions about grading or anything, send me a message on Slack. I will see everybody on Thursday.
Would it be a virtual God and Grub or no?
There should be. We really should have a virtual Bible study. I didn't even think about that. Next week. We're going to do this next week, Chris.
All right, let's do it.
All right. So plan on it. Next week, we'll have a virtual Bible study from noon to 1.
Or we can just worship Perel.
how will the Tech Talks work?
I believe
Question.
I reached out to the person just to make sure she's still game, so we'll do it as a Zoom.
Okay.
But I'm waiting to hear back confirmation to make sure that things are fine for her and she's not sick or doesn't have other priorities. I mean, because she runs a company, so it's entirely possible that there are bigger fish to fry right now. And if that ends up being the case, I'll just give everybody full credit for it, since you were expecting it as part of your grade, and we'll just move on with life.
Okay.
But as of right now, we're going to plan on still having it via Zoom unless I hear otherwise from her.
And of course, delays and whatnot, if like different times and what.
Yeah, I think the time will probably end up working fine. I mean, I think it's either it's still fine for her, or life is a little bit different now than it was when she agreed to do it, and we just have to take that into consideration and move on. So I'll let you know as soon as I know, but for right now, it's still the same time and date. It'll just be on Zoom instead of in person.
All right.
All right, I'll see everybody on Thursday.